Module 5, Geotechnical Engineering 1. The contents are here: shear strength of soil, practical applications, Mohr column failure criterion, Mohr Circle method, numerical problems, relationship between shear parameters and principal stresses, a brief discussion of direct shear test in the laboratory, triaxial compression test, vane shear test, unconfined compression test, applicability, and a few numerical problems based on UU-CD tests. Plus, you have the stability of finite slopes, wherein we'll discuss toe failure, base failure, slip failure, Swedish circle method, friction circle method, and the factor of safety with respect to cohesion and angle of internal friction. So basically, the fifth chapter is a mix of shear strength of soil and the stability of slopes. Shear strength. When you talk about materials, when you talk about the strength of materials, you have tensile strength, compressive strength, and shear strength. Tensile stresses, compressive stresses, and shear stresses. Strength is the maximum stress that a material can take just before failure. So tensile stress is the nature of stress when you apply an axial tensile load onto the material, as you can see in the first picture. You are trying to pull it apart, just like the way you test a reinforcement bar in a universal testing machine. Compressive test is a test that you do on concrete materials. For instance, concrete cubes are axially compressed to test whether it can take the designed amount of compressive load. Likewise, shear stress is a tangential stress that you apply. You don't apply axial stress, you apply tangential stress, just like this. Now, soil as a material is actually under compression due to its own load most of the times. But when this compressive force, or the force of gravity, which is vertically in plumb, is on an inclined plane, it will act as a shear force. So basically, even if the force is in the direction of the plumb or gravity, when it acts on an inclined plane, it gets the nature of a shear stress. So when you have a foundation kept on the ground or at a depth, and if there's a plane like this, the stresses on that plane will be shear stress. Quite similar to that, when you have a slope on an embankment, if you have an inclined plane, the inclined plane will be subjected to shear stress. So shear strength of the soil is maximum resistance to shear stress just before failure. The direct shear does not usually happen to a soil mass, but compressive load present in the soil induces shearing. So compressive load can either be due to its own weight, the self-weight of the soil, or perhaps due to the load that's applied onto the soil. For instance, a foundation, the superstructure applies a load onto the soil. So nonetheless, these compressive stresses or the compressive loads induces shearing. And the failure by shear occurs by relative movement of particles, like this. As you can see here in this picture, there's a chance for the relative movement of particles, which induces shearing. Now, to understand the shear stresses, we'll take a cylinder, a cylindrical sample. In this cylindrical sample of soil, you have major principal plane and a minor principal plane. Principal plane is a plane on which shear stresses is zero. So in this particular cylinder of soil, shear stresses are zero on the top and the bottom planes, and also the circumferential plane. The top and the bottom planes are the major principal planes, and the circumferential plane is a minor principal plane. A plane on which the maximum compressive stress, sigma 1, exists is a major principal plane, and a plane on which a minimum compressive stress, sigma 3, exists is called the minor principal plane. So in short, sigma 1, the major stress, is applied on to the top and the bottom plane, whereas sigma 3, the minor stress, is applied on the minor principal plane. So if you're familiar with the Mohr Circle concept in strength of materials, it'll be easy for you to understand this concept. I have the same cylinder in elevation here, and I have the major principal plane here on which sigma 1, major principal stress, is acting, and I have the minor principal plane, this plane, on which sigma 3, the minor principal stress, is getting applied. So I have axial compressive load and a circumferential load sigma 3. Plus we can take an inclined plane like this at an angle, let's say theta, with respect to the horizontal. So this bottom portion of this particular cylinder, when zoomed in, and if we draw the free body diagram, I can have sigma, the normal stress, acting on the inclined plane, and tau, the shear stress, acting on the inclined plane, and the inclined plane is at theta degrees with respect to the horizontal. One thing you need to remember is that the horizontal plane is a major principal plane and the vertical plane is a minor principal plane. And when you take an inclined surface, a cut surface within the sample, it'll be at an angle theta, let's say that, and that particular plane is acted upon by a normal stress sigma and a shear stress tau. So we can have an expression for sigma and tau in terms of sigma 1, sigma 3 and theta. The shear stress tau, component of the normal stress, causes the soil to move relatively and leads to failure. Or in short, sigma 1 and sigma 3 will have a threshold combination which causes shear stress and induces the failure by relative movement. And the relation for tau is sigma 1 minus sigma 3 by 2 sine 2 theta, and the relation for sigma on the inclined plane is sigma 1 plus sigma 3 by 2 plus sigma 1 minus sigma 3 by 2 cos 2 theta. We'll move to Mohr Circle. Now, Mohr Circle is the same thing that you might be familiar with in your strength of materials classes. The same thing gets applied to soil mechanics when you talk about the shear strength of soil. Mohr Circle, nonetheless, is a graphical method for determination of stresses, as you would probably be knowing. You have the normal stress sigma plot against the shear stress tau. The normal stress is along the x-axis and the shear stress is along the y-axis. We can consider a cylinder like this, and sigma 1 and sigma 3 are the normal compressive stresses, and hence they are plotted on the x-axis. So you have sigma 1 here and sigma 3 here, the major principal stress sigma 1 and the minor principal stress sigma 3. So sigma 1 and sigma 3 are compressive stresses and they are plotted on the x-axis, and they are normal stresses as well. And tau is a shear stress, and hence it can be plotted on the y-axis. Tau is a shear stress acting on the plane that's inclined at theta with respect to the horizontal. So I have tau here, I have sigma here, I have sigma 1 and sigma 3 acting on the major and the minor principal planes respectively, and considering this inclined plane, I can have a resultant as well, which I've marked in the red color arrow. So the resultant R is a resultant of two force vectors tau and sigma. So I can have the Mohr circle like this. The right side will have sigma 1 and the left side, the minor value, will be sigma 3. And I can have theta marked here, where 2 theta is the angle subtended at the center and theta is the angle subtended at the circumference. And here you have the point sigma comma tau. So in short, the normal stress sigma and the shear stress tau is represented by one single point on the circumference of the Mohr circle, which has sigma 1 and sigma 3 and sigma 1 minus sigma 3 being the diameter. So in short, the Mohr circle is drawn with sigma 1 plus sigma 3 by 2 as the center and sigma 1 minus sigma 3 by 2 as the radius. And a line is drawn at an angle 2 theta at the center or theta at the circumference, and this line will meet the circle at a point at the circumference whose coordinate is sigma and tau. So knowing sigma 1 and sigma 3 and also the angle theta made by the plane with respect to the major principal plane, which is the horizontal plane, the shear stress tau and normal stress sigma acting on the plane can be determined using the Mohr circle. So this is the advantage of the graphical method called as a Mohr circle. And you can have this example also to find sigma and tau. The only difference is that theta has an increased value here and 2 theta of course is double that value. So in short, when you draw a line at theta angle from this point, which is the origin of planes, it will meet the circle at a point whose coordinates is sigma and tau. So these two figures will help you understand how the graphical method of Mohr circle is very useful for us to determine or arrive at sigma and tau on a plane. A few points are marked here. You have the major principal plane here and the minor principal plane here. The same thing. Sigma 1 is here, sigma 3 is here, theta, the angle, is here, tau and sigma are on the inclined plane. And when you take a look at this example, this figure, you can see that sigma 1 plus sigma 3 by 2 is the distance of the center from the origin, and sigma 1 minus sigma 3 by 2 is the radius of the circle. So E, the point E, is the pole or the origin of planes, and stresses sigma and tau on the plane that makes an angle theta with respect to the major principal plane can be determined by drawing a line at the pole P, making an angle theta with the principal stress axis. This line will meet the circle at the point whose coordinates are sigma and tau. Mohr theory. The Mohr theory says that the failure is caused by a critical combination of the normal stress and the shear stress. So understandably, it just means that although the shear failure happens by shear stress at failure depends on the normal stress also. So when you have the cylindrical sample here, and when you apply a squeezing compressive load on its circumference and an axial compressive load on its set of major principal planes, it will create a combination of shear loads or shear stresses at the inclined plane. So a critical combination of the normal stresses sigma 1 and sigma 3 causes this sample to fail along the inclined plane. Or in short, shear strength S, which is a maximum shear stress the soil sample can take, is a function of the normal stress sigma. So this is a Mohr theory, and it says as S is a function of sigma, and the failure occurs when the Mohr circle touches the failure of Mohr envelope. So any Mohr circle with sigma 1 and sigma 3 that lies below the failure envelope, which is marked in the dotted line, represents a non-failure situation. But once the Mohr circle touches a Mohr envelope, failure takes place. And when sigma 1 and sigma 3 are such that it forms a Mohr circle of radius large enough to touch the failure envelope, the soil fails in shear. So take a look at this cylindrical samples picture and this Mohr circle drawn here. Mohr envelope is a maximum that any circle drawn can reach. There will not be any circle beyond the Mohr envelope. So let's draw first circle. Let's think that we are drawing first circle, which is a smaller circle here, with a sigma 1 and a sigma 3 value. And sigma 1 minus sigma 3 will be the diameter. So this small circle is well below the Mohr Coulomb envelope. So this small circle is safe. But when you increase sigma 1 and decrease sigma 3, you'll get a bigger circle. So this bigger circle will have a bigger diameter and it will reach the Mohr Coulomb envelope, and it just touches the Mohr Coulomb envelope and it fails. And when you further increase sigma 1, it means that sigma 1 minus sigma 3 will still have a further increased value, and it will have a very big circle, but that big circle can't be drawn because it will go above the Mohr Coulomb envelope, or you will not have an option to have a higher sigma 1. The soil will fail well before that. Assume that you are trying to load the cylindrical sample with 5 kilopascal sigma 3 and 10 kilopascal sigma 1, and it represents this small circle. And when you increase the sigma 1 value to 20 and keep sigma 3 as 5, the difference between sigma 1 and sigma 3 turns out to be 15, and it'll have a bigger circle that touches the Mohr Coulomb envelope, and it just fails, or it just starts to slide and gives failure to the soil. Which means that if you increase sigma 1 to 25, there's no chance to apply that load before, because the soil already failed. That is a concept given by the Mohr Coulomb envelope and the Mohr circle. So when sigma 1 and sigma 3 are such that it forms a Mohr circle of radius large enough to touch the failure envelope, the soil fails in shear. And the function of sigma is the shear stress or the shear strength, which is represented by this equation to be specific. S is a function of sigma, or S equal to C plus sigma tan phi, represented by this graph. This is the same Mohr Coulomb envelope that you saw in the previous slide, but represented mathematically in this graph. C is the intercept and phi is the slope of this line. S equal to C plus sigma tan phi is a very important equation, and it gives the shear strength of soil. C, the intercept, is a cohesive strength, and phi, the angle of internal friction, is the slope. These two terms, C and phi, are called as the shear strength parameters of soil, and they are inherent properties of the soil. C is a cohesive strength which represents the adhesiveness of the soil, and phi is an angle of internal friction which we determined from a few lab tests that are discussed subsequently in this chapter. In case of pore pressure measurements, the effective values of parameters are considered. S equals C dash plus sigma dash phi dash is when you have the pore pressure measurements. So S is the shear strength, C is a cohesive strength, sigma is the normal stress, phi is the angle of internal stress. The angle of internal resistance. And there are a few relationships between the shear strength parameters and the principal stress as explained in this graph. So this graph again is a Mohr circle drawn with sigma on the x-axis and tau on the y-axis. And let's mark a point sigma comma tau. It's a point on the circumference and it's a plane on the actual cylindrical sample. And the angle that this line makes is phi, the slope, and the intercept is C, the cohesive strength. And just like we discussed in the previous slides, you have theta marked here at the origin of poles and 2 theta marked here at the center of the circle. So I can have sigma 3 here and sigma 1 here, because that's what helps you draw the circle. Sigma 1 is a major principal stress, sigma 3 is a minor principal stress, and I can have these alphabets representing these points A, E, B, C, F, etc. and O is the origin, and the distances are marked here. You have C here and phi here. So when you take this particular triangle, you can have C cot phi as this distance, and the second distance marked here is the distance of the center of the circle from the origin, which is the average of sigma 1 and sigma 3. So you have sigma 1 plus sigma 3 by 2 is as this distance OC, and of course CF is the radius of the circle, which is sigma 1 minus sigma 3 by 2. So CF is equal to CB is equal to CE. The radius of the circle is sigma 1 minus sigma 3 by 2. And BE, the line BE is a failure plane represented in the Mohr circle, and B is a point indicating the stress on the failure plane, the actual failure plane. So B with the coordinates sigma and tau represents the failure plane of the actual cylindrical sample, and theta is the angle made by the failure plane, theta, the angle made by the failure plane BE with the major principal plane. A relation that you get connecting sigma 1, sigma 3 and the shear stress parameters from this detailed Mohr circle graph is sigma 1 equal to sigma 3 tan square 45 plus 5 by 2 plus 2c tan 45 plus 5 by 2. Sigma 1 is a major principal stress, sigma 3 is a minor principal stress, phi is the angle of internal friction, c is the cohesion. So c and phi put together are the shear strength parameters of the soil. The derivation of this equation is actually quite interesting from this graphical sheet, but it is not included in your syllabus. And the term tan square 45 plus 5 by 2 is called as the flow ratio in phi. And tan square 45 plus 5 by 2 based on trigonometry can rather be represented as 1 plus sine phi by 1 minus sine phi as well. Now this term is of importance when you study the lateral earth pressure of soil. Sigma 1 is equal to sigma 3 tan square 45 plus 5 by 2 when you have C equal to 0. So the soil type where C equal to 0 is called as a cohesion-less soil, or in short, the sand. So sigma 1 equal to sigma 3 tan square 45 plus 5 by 2 for sand, but tan square 45 plus 5 by 2 is 1 plus sine phi by 1 minus sine phi, which you'll see is as a different expression called Kp when you study the lateral coefficient of earth pressure. Now, from triangle ABC, this big triangle ABC, you can say that 2 theta equal to 90 plus phi. 2 theta equal to 90 plus phi. Also, you can say that theta equal to 45 plus 5 by 2.